Welcome all. Today we will start with the new lecture. The name of the lecture is Dynamic Properties of Ductile Materials. So, let us dive into it. So, what are ductile materials? As we have seen, the ductile materials are defined as a material that can be subjected to large strain before a fracture occurs. Okay. So, this is the property of the material. Okay. So, if you look into the stress strain curve, okay. So, first comes the elastic regime. After the elastic regime, the plastic regime starts to occur. Okay. And after certain plastic strain, okay, the material fractures. Okay. So, if this region is large, okay, then this is said to be a ductile material. Okay. If you compare two materials, okay, having the roughly the same elastic properties, but the fracture point occurs before the one. Okay. Let us say this is material 1 and this is material 2. Okay. So, here the fracture of the material 2 occurs early than the material 1. So, material 1 is said to be more ductile in nature as compared to material 2. Okay. So, what are the different properties of the ductile material? Ductile material can absorb large amount of energy that we have seen already. The area under this curve is considered as the total energy absorbed or the efficiency of this material in energy absorption. So, larger the area, the larger amount of energy absorption occurs. Okay. So, due to this property, the ductile materials are suitable for shock absorbing application or energy absorbing applications. Okay. They undergo significant deformation. As we can see, since the strain is large, it means that they are undergoing large deformation. Okay. They exhibit necking before fracture, providing visible warning signs before failure. So, what is necking? So, let us say we have a material which starts like this. Okay. There is no deformation. Okay. It is held between two pieces. Okay. So, as the deformation occurs, okay, as this thing is pulled apart, okay, the material tries to become thin at the center. Okay. And so, this can be considered as the starting stage. Here this can be considered as the final stage where the end point occurs, and after this point the fracture of the material will occur. Okay. So, this phenomena, okay, where this type of curvature is formed, and this is called neck. Okay. So, this is called a necking. So, this shape which occurs before the fracture is called necking. Okay. So, visually also we will get a warning that the material is about to failure. This is in contrast to a brittle material. In a brittle material, this type of necking will not occur, okay, and will not get any visible warning that the material is going to fail. Okay. So, that is why always a ductile type of failure is designed as compared to a brittle type of failure. Okay. So, the different type of materials that exhibit ductile behavior are commonly all the metals, or roughly almost all the metals will exhibit this ductile type of behavior, like copper, aluminum, steel. Okay. They will exhibit ductile type of failure. Their stress strain curve will be something like this. Okay. And this type of materials has a wider application in structural and impact prone applications. Okay. So, steel, aluminum, copper. So, steel is widely used in design of the buildings, aluminum in aircraft or the vehicle bodies. Okay. So, this has a wide applications in the structural field. Okay. Different type of alloys also exhibit ductility, like brass, bronze, titanium. Okay. So, what happens is that the ductility of the metals is combined with the high strength capacity. Okay. So, they exhibit ductility also, okay, this large region, as well as the sigma y, okay, or the sigma also goes up. Okay. So, alloys are the mixture of this different type of metallic properties where the strength as well as the ductility is being combined together to exhibit a efficient material. Okay. So, this type of things are common in aerospace, automotive field and the defense industry, okay, owing to their lightweight and being more resistant to fracture or any other given failure modes. Okay. Moving ahead. So, now we have seen ductile material. So, in contrast to the ductile material, we will look into the brittle material. So, brittleness is one of the material properties where the breaking of the material will take place without any deformation, even though the material is hard. Okay. So, if we look into two different materials, okay. So, this is a ductile behavior, and this becomes a ductile behavior, and this becomes a brittle behavior. Okay. So, what happens here is that the breaking of the material, okay, there is a sudden breaking of the material will take place, and the deformation will be very less. Okay. The material will be hard. Okay. The material is not going to soften up or anything, but it will suddenly fail. So, this behavior is called the brittle behavior. Okay. So, key traits of the brittle materials, they break without noticeable plastic deformation. Okay. So, here we can see in the ductile material there will be a significant plastic deformation. In the brittle material, the deformation will be very less. Okay. And the plastic deformation is almost negligible. Okay. Traditionally, the brittle materials will have high compressive strength, but they will have low tensile strength. Okay. As in case of conventional concrete, the concrete is very good in taking compression. Okay. If we compress it, it can take a large amount of load, but in contrast to that, if it is subjected to any sort of tensile loading, it will fail abruptly. Okay. So, this type of materials are also susceptible to crack initiations. The cracking occurs in this type of materials. Okay. And it will propagate through the body of the entire system. Okay. In case of ductile material, we have seen that necking region will form. Okay. And this necking region will give us a warning. Okay. Warning of when to expect the fracture. So, in ductile material, we have seen that the necking will give us a warning. Okay. So, if this neck is very thin, then we can assume that the fracture is going to occur. In brittle material, no neck is going to form. Okay. So, this is a system which fails without any warning system. Okay. And due to its limited area under the stress strain curve, it has a limited ability to absorb energy. Okay. So, the examples of brittle materials are cast iron, ceramics, glass, concrete. Okay. So, these are some of the common examples of a brittle material where the energy absorption is low and it fails without any warning. Okay. So, these are some of the failure modes which we can see during the failure of these materials. Okay. Moving ahead. So, difference between brittle and ductile material. Okay. Brittle material. Okay. So, what are the properties that the brittle material will exhibit as compared to the ductile material? The brittle material will break when we try to bend it. The ductile material will have a larger resistance towards bending. Okay. So, we will try to understand this thing, what happens during bending. So, if we take two materials, okay, made up of ductile and non-ductile material. Okay. So, in ductile material, okay, the top piece, okay, or the top surface will be under compression and the bottom surface will be under tension. Same thing also happen in the brittle material, compression and tension. So, as we have seen earlier, the brittle material cannot take tension. Okay, it is very poor in taking tension. Okay. So, the ability of this material to take bending is very less. Okay. So, that is why this things comes into picture. Okay. So, if you can see, if we try to make a beam made up of entirely concrete, or if a glass sheet is there, okay, if we try to bend it, it will break suddenly. Okay. But if we take a metallic beam, okay, then it can take the bending. Okay. What happens when we try to machine a brittle material? Okay. So, the chip formation will be non-continuous. Okay. What does it mean? It means that the breakage in the chip formation will take place. Okay. If we try to machine, okay, or if we try to give a shape through any machining process, okay, there will be breakage in the material. Okay. But if you try to machine a metal, okay, then we can have a very smooth and continuous surface. Okay. There will be no chipping observed. Okay. This is again due to its inherent inability to take any sort of tensile load. Okay. So, brittle material have high Young's modulus, ductile materials comparatively will have a lesser Young's modulus. Okay. The break in the brittle material will occur without any sign of crack or breaks. Okay. So, we have seen the stress strain curve will be having this thing. Okay. So, there will not be any warning, okay, and there will be no warning sign, and it will abruptly break. So, but in a ductile material we can see that the entire propagation of the material will occur. Okay. Brittle material will yield before the fracture point, okay. Ductile material will deform before the fracture point. So, if this is the fracture point, okay, then it has deformed significantly. So, before the fracture point there will be a significant deformation in the ductile material, and in a brittle material what will happen is that before the fracture point only the yielding portion will come into picture. Okay. So, brittle material are traditionally have low energy absorption as compared to a ductile material, okay, and their inability to take the tensile loads make them vulnerable for any machining process, okay, or design of any type of energy absorbing materials. Okay. So, here we can see a comparison of the brittle and the ductile materials. Okay. So, if we are in the right hand side regime, the material is ductile, and if we are in the left hand side regime, the material is brittle. Okay. And this regime is being bifurcated by the elongation property. So, larger elongation will give us ductile material, less elongation will give us the brittle material. So, any sort of foams, rubbers, polymers, okay, they have traditionally large amount of deformation. Okay. So, they are considered as the ductile material. Any type of ceramic, porous ceramics or glasses, okay, they have a very less deformation ability. So, they are considered as the brittle material. Okay. Metal and alloys, they are also ductile and they form in the mid range properties. Okay. So, they are more towards the ductile material. So, moving ahead, stress strain curve for brittle versus ductile material. So, this is the graph that we were dealing. Okay. So, in the brittle material there will be certain break with little deformation. So, a brittle material, it will try to undergo the elastic deformation and it will suddenly fracture, okay, it will suddenly break. In comparison, a ductile material will undergo large deformation and then it will fracture. Okay. So, if you take this type of coupons for the ductile materials, okay, so the ductile materials will undergo significant necking, okay, and after that necking this fracture will take place. In a brittle material, the necking will be almost non-existent, okay, it will not neck and it will suddenly break. So, this is how the coupon of a brittle material will look like, and this is how a coupon of a ductile material will look like. Okay. And the area under this curve is the total energy absorbed, which is more for a, or which is significantly more for a ductile material as compared to a brittle material. Okay. So, basic mechanical properties of ductile material, they have a high ductility. It means that they can undergo large plastic deformation before fracture, and this is measured by percentage elongation. It means that before fracture occurs, okay, it can undergo large deformation. Okay. So, it has undergone large plastic deformation and this is measured in the percentage elongation. Okay. So, total elongation, okay, or total increase in length by the initial length. Okay. So, high toughness, it absorbs significant energy before breaking. So, the area under the stress strain curve is large, okay, it is significantly large. So, they have high toughness, okay. They have moderate to high tensile strength. Traditionally, metallic materials, okay, exhibit ductile behavior and they have moderate high to tensile strength. For example, normal steel will have a normal tensile strength of around 450 to 500 MPa. Okay. Hardened steel can go as high as 1000 MPa also. Okay. So, these are the moderate tensile strength. Okay. but they will exhibit significant ductile deformation, okay, and the brittle fracture under the loading will not occur. So, the metals will not behave like this, okay, they are going to behave like this, okay. So, the ductile material will exhibit high plasticity. It means that they can undergo permanent deformation without rupture. So, this is very much required for the forming process, okay. So, in the forming process, if some shape is required, okay, if some annealing process or something, if some shape is required, so it can be only achieved by the ductile material. If a brittle material is tried to give shape, either some chipping will occur at the surface, so it will form a non-continuous layer, or it will break suddenly, okay. So, for this type of forming process, the ductile materials are required, okay. So, low to moderate yield strength. So, they again comparing from the previous one, they also have low to moderate yield strength, okay. So, high strain hardening, okay, material strengthened during deformation, okay. So, increasing the load capacity. So, here we can see that there is a hardening process out here, okay. So, there is a hardening regime, okay. The material will become, the stress will increase, okay. So, this is called the hardening process. So, this will be exhibited in a ductile material, okay. So, it has a ductile fracture behavior. It means that there will be a whizzing necking and a cup on cone things will occur, okay. So, if it starts like this, okay. So, before fracture this thing will form, okay, a necking region will form, and this is a more safer and predictable mode, because upon seeing the necking regime occurs, we can predict that the failure is now imminent, okay, and due measures can be taken to safeguard against the failure. But in a brittle behavior, since this fails suddenly, so there is no necking and it will abruptly break out, okay. So, there is no visible warning portion, okay. So, normally a ductile type of material is used for an energy absorbing system, okay. Moving ahead. So, basic mechanical properties of a ductile material. So, different type of regimes are being defined here. So, here the first point is the proportional limit, okay. Proportional limit means, okay, the stress is directly proportional to strain. It means stress equals to some proportionality limit constant times the strain. So, this is called the Young's modulus, okay. After this point, the elastic limit is reached. Elastic limit means if I release the stress at this point, it will go back to my original shape, okay. But here in this region, the elastic stress might not be directly proportional to my strain, okay. So, this is the proportionality limit first. After that, my elastic limit is there, okay. So, just after the elastic limit, my yielding in the material will occur, okay. So, the yielding will take place. So, these are the three different points, okay. So, this is considered as the elastic region. The first region is called the elastic region. After this point, the yielding will start to occur, okay. So, after the yielding stress, there will be a increase in the stress, okay, stress seen by the material. So, this region is called as the hardening region, okay. Okay. So, after the hardening region, the necking will start to occur, okay. So, these are the different regimes here, okay. Increase in the stress, okay. So, that stress value is called the ultimate stress, and the stress at which the finally after necking the system breaks apart, okay, that thing is called the fracture stress, okay. Now, here we can see there are two graphs, okay. One it is coming down and one that is coming up, okay. So, we will try to see this behavior. So, what is happening in the first graph, okay. So, in the first graph what is happening is, if I take a coupon, okay. So, this type of pieces that are used for testing, they are called coupons, okay. So, in the coupons what happens is that they are gripped at this end, okay, in a universal testing machine, and they are also gripped at the other end, and this thing is tried to pulled. Okay. So, the total amount of force is monitored here, okay. And here there are strain gauges that measures the change in length, okay, or the increasing length is measured. Okay. In this axis and this y axis, okay, change in length, okay, or the increased length divided by the original length is being measured. Okay. And in this graph, sigma, okay, the force applied divided by area is being recorded. Okay. So, there can be two areas here. Okay. One area is the initial area A naught, okay, and other is the, so we know that the necking is going to occur. Okay. It means that the cross sectional area is going to decrease. Okay. So, if we plot force divided by the actual cross sectional area, okay, then the true stress strain curve is obtained, which is this one, and if we take the original area, then the engineering stress strain curve is being measured. Okay. So, this is how these two things can be represented. Okay. One is the true stress strain curve and other one is the engineering stress strain curve. Okay. So, we now look into the overview of the energy absorbing systems. Okay. So, the purpose of the energy absorbing systems, as we have been clearly seeing for the past lectures. So, these systems are engineered or they are made to mitigate and dissipate kinetic energy from impact, blast or dynamic loading to prevent structural failure or injuries. Okay. So, here we can see a crash barrier in which a car hits. Okay. So, here the first order of this energy absorbing device, okay, will be to protect the injury to the occupants, okay, then protect the vehicle, and if possible then save the energy absorbing system also or any peripheral systems that are required. Okay. So, occupancy protection, vehicle protection and any other third party protections are required. Okay. So, this is a finite element simulation of the same thing. So, as we progress in the course, we will try to see whether we can do certain type of simulation and evaluate the efficiency of a crash protection system. Okay. So, the different type of crash protection systems are crash barriers. So, they are nothing but roadside or rail track barriers that are designed to absorb the vehicle impact. Okay. So, we have seen the vehicle. Okay. So, normal vehicles are around 2 tons, okay, and they travel at a velocity of 60 kilometer to 70 kilometer per hour. Okay. So, this amount of energy has to be absorbed by the energy absorbing systems. So, crash barriers are designed to withstand this much of energy. Okay. Then there are sacrificial cladding systems. Okay. So, they are thin replaceable panels, okay, that deform under blast or impact load to protect the structural core. Okay. So, what happens is that if this is my structure made of concrete or other steel panels, okay, okay, then one sacrificial cladding system is being added out here, okay, which is made up of steel plates, okay, or any other type of hard material, okay, and inside this some sort of soft core material or honeycombing material or any other type of new materials are being used. Okay. So, if a blast or impact occurs out here, this thing will try to distribute the energy over a large area and the other soft core or the interior core will try to absorb this energy through plastic deformation. Okay. And using this mechanism, the total amount of energy will be absorbed by this sacrificial core and it will prevent the transfer of the energy from the impact or the blast event to this core event, okay, thereby protecting the core. Okay. So, this type of cladding systems are called the sacrificial cladding system. So, after the event this can be replaced and a new one can be put in the place. Okay. Similarly, blast resistance panels are used. Okay. So, what happens is that in defense sectors, okay, so there are different configurations where the blast resistant panels are being used. Okay. So, what happens is that similarly for a sacrificial system is a one time usage system. blast resisting panels, okay, or the permanent panels, they can be used multiple times, okay. So they have a higher resilience or the higher energy absorption capacity. So they are not destroyed entirely after a single event, but they can be used for a multiple event purpose also. So as we progress in the course, we will see how to design this type of systems, sacrificial systems also, and the blast resisting systems also. Okay. So the design principle, so the design principle is the same as we have been learning throughout the previous classes also. So materials in this system must undergo controlled deformation to absorb and redistribute the energy effectively. Okay. So ductile materials are ideal due to their plastic deformation capacity. So as we have seen, what happens is that first of all there will be a hard plating, okay, which will distribute the impact or the blast energy to a larger surface area. So this will be a hard plating type of system, and after that there will be an soft energy absorbing layer, okay, which will undergo large plastic deformation. So this material will undergo large plastic deformation and it will try to absorb the energy, okay. And there will be a third layer also, okay, which will try to mitigate, okay, or it will minimize the transfer from this layer to the other protective layer, okay, be it a helmet, be it a protective body armor, be it a structure. So the transfer of the energy from here to here will be minimum, okay, and that will be ensured by the inside plate. So hard plate for distributing the total amount of energy, soft core for absorbing the energy, and the inner core to minimize the transfer of the energy, okay. So traditionally these three configurations are used and different type of materials are used to achieve this system, okay. Moving ahead. So failure mode in ductile material. So there are different types of failure mode in the ductile material. So we will try to see during a dynamic event what are the failure modes occurring, okay. So first is the necking. So necking we have been seeing for in the previous stages also. So there is a localized reduction in the cross sectional area during tensile loading. So as we have seen the example of the coupon, so we started with this type of coupon, okay, and we tried to pull this thing, okay, keeping this thing fixed. So what happens is that in the cross sectional area, okay, in this region is going to decrease, okay. So as the pull increases, the cross sectional area will try to be minimum and minimum, and after certain time the fracture is going to occur, okay. So this behavior is very common in steel, okay, or any metal, steel, aluminum, this type of necking will try to occur, okay. Then comes ductile tearing, okay. So what happens during ductile tearing? So there is a progressive crack growth accompanied by fracture here, okay. So the plastic deformation, some sort of cracking will initiate it, okay, and this crack will be accompanied by the plastic deformation, okay. So some sort of cracking initiation will take place and it will try to propagate through and through, okay, and this propagation will result in the failure of this ductile material, okay. So this results in a cup and cone fracture appearance, okay. So it will look like a cup and cone type of fracture, okay. So strain localization and the void coalescence, okay. So at high plastic strain, voids nucleate and coalesce to form cracks, okay. So what happens normally, okay. So in case of impact, there will be what will happen, this will happen in case of highly localized events like an impact. So there are inbuilt impurities present in the ductile material. So what these impurities will do is that it will try to form the voids in the metals, okay, and these voids will start to grow, okay, and once it grows, okay, there will be a localization of this growth of the voids in certain region, okay, and if you look closely in a microscopic layer, there a necking formation will occur inside this voids, okay, and after the necking is occurring, okay, this voids will come together and surface cracking will form in this void necking region. Okay. So, this is called the coagulance of the voids. Okay. So, from the impurities the voids will grow, the voids will form neck, and from the necking the fracture, the internal fracture in the necks will occur. Okay. And eventually the material is going to fail. Okay. So, these are the different types of failure which can be observed in a ductile type of material: necking, ductile tearing, and the strain localization and the void coagulance. Okay. So, I will stop here. Thank you.